This video is one in a series that explains how to use the program comprehensive meta-analysis. This video works with correlations. There are others that work with means and proportions. These are some of the videos in the series, and the one that you're looking at right now explains how to run a basic analysis. I'm going to use the data set that we have in our book, Introduction to Meta-Analysis. In the earlier video, I showed you how to enter the data for these 6 studies. We have, for example, Fonda. Correlation is 0.5, sample size is 40. The program automatically reflects back the correlation, computes the standard error and the variance of the correlation, and it also shows the corresponding values using the Fisher-Z transformation. To run the analysis, we simply click on the button that says Run Analysis. What we see over here is the 6 studies. For each study we see the correlation, the lower and upper limit, the z-value, the p-value. We see that over here also as a forest plot. Let me change the scale to go from -1 to +1. So for example, for Fonda, the correlation is 0.5. The confidence interval goes from 0.22 approximately to 0.7. As is always the case, when we're dealing with correlations, 0 reflects the null hypothesis. If the confidence interval overlaps 0, the p-value is going to be greater than 0.05. If the confidence interval does not include 0, then the p-value is going to be less than 0.05. So we can see over here, where the confidence interval does not include 0, the p-value is less than 0.001. For this one over here, where the confidence interval just almost touches 0, the lower limit for the confidence interval is 0.006. The p-value is 0.047, just a touch away from 0.05. Down here we have the overall, the combined effect, which is a correlation of 0.34 with a confidence interval of 0.268 to 0.408 and a p-value of less than 0.001. At the moment where you're using the fixed effect model, that's indicated down here by the fact that the tab mark fixed has been is in bold. Now there are any number of things that we can do working with this screen. One thing is we can click over here, and the program is going to show us the weight that is assigned to each study under the fixed effect model. We see, for example, that this study over here gets 65% of the weight. In other words, for purposes of computing the combined effect, 65% of the information that goes into computing this value is taken from this study, whereas this study over here contributes only about 4% of the information. Obviously, therefore, this study is going to be given a lot more weight in the analysis, and this one is going to be given relatively little weight. The reason for that depends on a couple of things, but it's primarily based on the sample size. If we come over here and click on this button, we can see that this study has a sample size of 400. This study has a sample size of 25. Just to make this a little bit easier, let's compare this to this study up here. This has a sample size of 400. It gets about 65% of the weight. This has a sample size of 40. It gets about 6% of the weight. So the weight is roughly proportional to the sample size. It's a little bit more complicated than that, but that's the basic idea. Some other things that we can do with this. The basic difference between the fixed effect model and the random effects model is under the fixed effect model, we begin with the assumption that all of the studies really have the same true underlying effect. And any variation that we see from study to study is just due to sampling error. In some cases, that is a viable assumption. In some cases, it is not really a reasonable assumption. But if it is a reasonable assumption and we apply the fixed effect model, then since all of the studies are estimating the same quantity, then it makes sense to give more weight to the studies that have more information about that quantity. Under the random effects model, in contrast, we don't make the assumption that all of the studies share the same effect size. Rather, we allow for the possibility, or the probability, the likelihood actually, that the true effect underlying each study is going to be different. And therefore, when we're using, for example, this study over here to estimate a single effect, we're no longer trying to estimate a single common effect. Rather, what we're trying to estimate is the mean effect across all possible studies. And now the error, the imprecision in using, let's say, this estimate over here as an estimate of this, is not only the within study error, the fact that the correlation that we observe in a study is subject to sampling error, but it also reflects the imprecision that comes from the fact that this particular study is basically one study among any number of studies that could have been done. It's easiest to see this if you think of it this way. Under the fixed effect model, all of the variation that we're looking at comes from within study error. So if all 6 of these studies, if each of them had an infinitely large sample size, then all of them would have identical correlations, because we are asserting that the true correlation in all of the studies is the same. And these effects would all line up one right on top of the other. Under the random effects model, what we're saying is that if we had an infinite sample size for each study, the effects that we observe would still not be exactly the same. There would still be some dispersion among them, because the true effect in each study is different. And what we're trying to estimate is not a single common effect, but rather the mean of any number of true effects. When we move from the fixed effect to the random effects model, we can see what happens. Down here, I'm going to click on random effects. The first thing that happens is that the weights become much more evenly distributed. And the second thing that happens is that the effect size shifts, and finally the width of the confidence interval shifts. And to see how that happens, what I'm going to do is come back here and click both models so we can look at the differences between them. Under the fixed effect model, the correlation was 0.34. Under the random effects model, the correlation is 0.49, which is quite a bit larger. Under the fixed effect model, the confidence interval was pretty narrow. Under the random effects model, the confidence interval is much wider. Now, why does that happen? First, let's focus on the effect size itself. Under the fixed effect model, because the only source of error is the within study error, we give a lot more weight to studies with a large sample size and a lot less weight to studies with a small sample size. So this study over here got 65% of the weight. This study got only about 3% of the weight. When we move to the random effects model, there are now 2 sources of error. There's within study error and between study error. And the second component, the between study error, applies to all of the studies. And therefore, whereas over here there was a major difference in the precision of this study versus this one, over here there's less of a difference. Because while if we're looking at the within study error, this study has a lot more error than this one. But if we're looking at the between study error, they both have the same amount of error. So when you add those 2 components together, the difference between them dissipates. And these are going to get more even weights. Another way to look at that is that if we're looking at a fixed effect model, this study with 400 people has 10 times as much information as this study up here. When we're looking at the random effects model, this study over here, while it might be a better estimate of the effect size in that particular population, but there's nothing to say that this particular population falls near the mean of all possible populations, and therefore we don't want to give it too much weight. By exactly the same logic, this study up here might be a very poor estimate of the effect size in this particular population, because the sample size is only 25, or over here it's only 40. But while this might be a poor estimate of the effect size in a particular population, that study is the only estimate that we have of the effect size in that population, because it's the only study that we have from that particular population. Therefore, we don't want to give it too little weight. So the bottom line then is, under the fixed effect model, the large studies get a really big part of the weight, the small studies get a trivial amount of weight, whereas under the random effects model, the large studies are still going to get more weight than the small studies, but the differences are not going to be nearly as sharp. So what happened over here? Just by coincidence, in this set of studies, the study that had the most people in it, the Granger study, just happened to have a really small correlation. The correlation over here was only 0.20. So under the fixed effect model, we give that study a lot of weight. It takes the effect size and pulls it way down towards 0.20, and we end up with a correlation of 0.34 overall. By contrast, under the random effects model, this study is only given about 20% of the weight. So while it still tries to pull the correlation down, it can't pull it down as much as it did under the fixed effect model. It has less of an impact, and the overall correlation is more of a reflection of the sort of the consensus among the other studies, and is less impacted by this one. Obviously, this is just the way it happened to work out in this set of studies. Had it been the case that Granger had a really high correlation, then this would have been exactly the opposite. The overall effect would have been larger under the fixed effect, instead of being smaller under the fixed effect. So the idea that the correlation is going to be smaller or larger depends. It really is a case-by-case basis, but the idea that it's going to be pulled, that the large study is going to have more of an impact under the fixed effect model is always true. The next thing we can look at is the confidence interval. The confidence interval is much wider under the random effects model than it was under the fixed effect model. The confidence interval is always going to be wider under the random effects model, because under the fixed effect model we say that there's only one source of error, that is the within study error, and that is whatever it is. By contrast, under the random effects model, we have the within study error plus an additional source of error, the between study error. And if you have more error, then obviously you're going to have less precision and a wider confidence interval. One other thing I find helpful is that right now we're looking at the relative weight assigned to each study. We can also click over here and look at the actual weight assigned to each study. So for example, in computing the fixed effect model, we applied a weight of 37 to the first study and a weight of 47 to the second study. In working with the random effects model, we applied a weight of 9 to the first study and about 10 to the second study. I like to think of the raw weight as the amount of information that is contributed by each study. The more information you have, the more precise the estimate is going to be. And you'll notice that the weights over here under the fixed effect model are always larger than the corresponding weight under the random effects model. Because if by information we mean the precision of the estimate, if we assume there's only one source of error, then the precision is always going to be greater under the fixed effect model. So if we add up these weights, we're going to come up with a larger number, more information, than if we add up these weights. That's why the confidence interval for the fixed effect model is always going to be more narrow, showing greater precision as compared with the confidence interval for the random effects model. So the raw weights, this column and this column, affect the width of the confidence interval. By contrast, if we're looking at the point estimate, then it's really the relative weights that matter. The studies that are assigned more weight are going to have more influence on whether this estimate moves to the left or to the right. And as I showed you a minute ago, that's why a very large study is going to have more impact under the fixed effect model and pull the point estimate toward it, whereas it's going to have less impact under the random effects model. But while sort of working through this example, I hope that I've been able to sort of show how you can use these little things over here to get a better understanding of what's going on in the analysis. Let me turn to some other things. There is a button up here you can press that says Next Table. When you click on that, you get sort of the same information that we had on the previous screen, but now you get it in a different format. Here we have the fixed effect model, and here we have the random effect model. In each case, you have 6 studies. You have the point estimates, 0.34 for fixed effect and 0.49 for random effects. You have the lower and upper limit, the z-value, and the p-value. Everything over here, everything that I just pointed out, refers to the test of the null hypothesis. All of this is really dealing with this and asking what is the point estimate, the confidence interval, What is the p-value for the test of the null that the actual correlation is 0? And I'm sorry, the actual correlation is 0. That would be over here. Clearly, there's no overlap. This does not overlap 0. The p-value is less than 0.001. And similarly, for this, we're talking about an effect size of 0.48 with this confidence interval. Clearly does not overlap 0. And over here, those are the numbers, 0.49, lower and upper limit, z-value of 4.0, p-value of less than 0.001. So all of that relates to the null hypothesis that the effect size is 0. Everything to the right of this, the part marked heterogeneity and tau square, relates to the question of the heterogeneity of the effect sizes. And let me show you what I mean by that. What we're looking at over here are effect sizes that vary. One here, one here, one here, and so on. Clearly, they are not lining up one directly on top of the other. But the question is, the dispersion that we're seeing, is that something that might be simply due to chance, to sampling error, or does it reflect a real difference in the effect size and the correlation from one study to the next? The point is that if we had 6 studies, and if in fact the true correlation was identical in all of them, we would not expect all of the effect size, all of the correlations to line up one on top of the other, because due to sampling error, one would be a little bit higher than the true value, one would be a little bit lower than the true value, and so on. Is it plausible that all of the dispersion that we're seeing over here can be due to simple sampling error? Or is it the case that there must also be some real differences in the correlations, that some of these studies used populations where the correlation was higher, where the true correlation was higher, and some used populations where the true correlation was lower? To put that in a slightly different perspective, let us imagine for a moment that each of these studies actually had an infinite number of people in it. Would it then be the case that all of the correlations were exactly the same? In other words, they really all do share a single common effect? Or would it be the case that there would still be variation from one effect size to the next? Well, this Q statistic over here, along with the degrees of freedom and the p-value, address that question. The Q statistic is 31 with 5 degrees of freedom and a p-value of 0.001, which tells us that it's very unlikely that all of the dispersion that we're seeing over here is due to chance. Put another way, if in fact we had 6 studies of the sizes that we see here, and all of them really shared the identical correlation, and we were to run 1,000 studies of draw 1,000 samples from those studies, the chances that any one of those meta-analyses would yield the amount of the dispersion that we're seeing here is less than 1 in 1,000. It's less than 0.001. And therefore, we would reach the conclusion that the null hypothesis of homogeneity is false. It is not plausible to assume that all of these studies share the same common effect size. And we will move on to the alternative, which is that there is dispersion in the true effects over and above whatever dispersion there is due to sampling error. The Q statistic, degrees of freedom to p-value reflect that. I square is a proportion. It's 84%. And what that means over here is that, okay, we're looking now at this, let me just select only the random effects model. We're looking at this amount of dispersion. Some of that is due to sampling error, and some of it we're saying is due to real differences among the studies. This is the amount of dispersion that we see. If we got rid of the sampling error, if we reran these studies with 1 million people in each one and plotted it, we would still expect to see some dispersion in correlations, but not quite this much. The fact that I square is 85 tells us that the pattern of dispersion, the variance specifically of the dispersion, would be 85% as wide as the dispersion that we're seeing here. So the dispersion would shrink, but it would not shrink by all that much. The variance of the dispersion is called tau square. The standard deviation of the dispersion is called tau. And these numbers First of all, they reflect the variance of the true effects, not the observed effects. In other words, if we were going to go back and actually compute the variance of these effects the same way that we would compute the variance for subjects in any primary study, that would be the observed variance. That is not what we're working with over here. We're using various formulas to pull out the dispersion that we think could be explained by sampling error. We take the remaining dispersion, which is the true dispersion, we compute the variance of that, and that value is 0.081, and the standard deviation of the true dispersion of the true effects is 0.28. I need to point out that these numbers over here, 0.081 and 0.28, are not in units of correlation, they're in units of Fisher's z-score, and we will get to that in just a minute. Okay, so I've covered the basics over here of how to do a simple analysis. Now, I should also point out that you can modify this screen somewhat. For example, over here, I can right-click over this and select Customize Basic Stats. So if I want to get rid of the lower and upper limit, for example, and the z-value, I can do that, or I can put them back in. I am not a big fan of p-values at all, but sometimes you need to have the p-value, and it might not be enough to display it to 3 decimal places. I don't think there's much of a difference between the p-value of 0.001 and 0.0001, but if you actually wanted to display the number of p-values over there, you could say I want to display 9 decimal places for the p-value, and you'd get that printed out over there. The point is simply that you can modify these things and customize them to meet whatever particular needs you're trying to address. There's a button up here that lets you look at the basically the residuals. So, for example, if we have a study like this one, which is minus 1.27, that tells you that given that if we're going to consider this the mean effect, that this falls somewhere out in left field. And typically, if you get a residual over here which is greater than 1.96, you might use that to identify an outlier. The fact that a study is an outlier does not mean that the study is incorrect, but it's a way of flagging studies that you might want to take a closer look at. It's especially useful in pulling out studies. If you're going to take a closer look at them, you want to make sure, first of all, that the data were entered correctly and you're not simply trying to make conceptual sense out of what was basically a typographical error. I can get rid of that. I'm going to point out very quickly, you also have this tutorial up here that you can use to sort of walk you through many of the issues that I'm discussing right now. Okay. While the analysis that we're looking at is an analysis of correlations, and that's generally the way you're going to enter the data and the way you're going to report the data, the fact of the matter is that using the Hedges-Olkin approach, which is what we are doing here and which is what most texts do, we don't actually do the analysis on the correlations. In other words, we don't take a weighted mean of these numbers over here. Rather, what we do is we convert each correlation into its corresponding Fisher z-score. Sort of, this is analogous to what you might do when you take a risk ratio and convert it to a log risk ratio. We're simply converting this to another scale. In fact, if you come back to data entry, you'll see that whenever you enter the correlation, the program computed the corresponding value of Fisher z. And if you're curious about how that's done, you can always double-click on that, and the program will show you the formula that it uses to do that. Possibly more helpful is the fact that in the book we work through this example in great detail, showing all the formulas and working them out in a spreadsheet. But the key idea is that all of the analyses are done in the Fisher z-scale. So in order to see how that works, and this is probably the only reason you would want to bother doing this, we can click over here and say, rather than showing me the correlations, show me the Fisher z-scores. What happens now is that rather than seeing a correlation of 0.5, we see a Fisher z of 0.549. Coming back here, it's no longer 0.5, it's now 0.549. The variance, similarly, is the variance of Fisher z, which is 0.027. And the standard error, so 0.027, if we come back here, we're now looking at a variance of 0.027. These are the numbers that are being used to do the analyses. What happens is the program takes a weighted mean of these numbers, uses that to compute the overall effect size, and then if you have selected Fisher Z, it simply shows that overall effect size down here, which is 0.354. If you selected correlations, it converts that back to 0.34, which is the correlation value for that. By the way, we're looking at fixed effects right now. I changed that before without mentioning it, so I apologize if I confused anybody. But that's the basic idea. So if you, generally you're only going to ever bother with the correlations, but if you want to understand the mechanism behind this, you can switch to Fisher's Z. You see over here all the numbers as Fisher Z. Then you can come over here to the calculations tab, and you can see how the calculations were done. The first study had a point estimate of 0.549 in Fisher Z units. I'm going to switch to random effects again. The variance for that was 0.027. The toss square is 0.081. Remember, if we go to the next table, toss square over here was 0.081. That is the number that is being used. So to get the total variance for the first study, we take 0.027 plus 0.081, and we get a total of 0.108. That's the variance for the first study. To get the weight for the first study, we take 1 over 0.108, and we get 9.266. If you come back to the main screen, we said it's 9.266. We come back over here. We show the raw weight, 9.27. which is the same, obviously, as 9.266, except for rounding error. We come back over here, and you can see the program for each row, for each study, it computes the weight, and then T times W is simply the weight times the effect size. So this would be 9.26 times 0.549, gives us 5.09. We do that for the weights, and we sum the weights. We sum the weighted point, so this is each point times its weight. If we sum this, we get 31.2. If we sum this, we get 58.9. And the way that you compute the point estimate is the sum of this column divided by the sum of this column. So it's 31 divided by 58, which gives us 0.53. That's our effect size in Fisher Z units. And to get the variance, we simply sum the W's. That's 58. 1 over 58 gives us 0.017. That is the variance of Fisher Z units. And then the last thing that we need to do is to switch back from Fisher Z to a correlation. And the correlation is 0.485. Now you'll notice when we switch back to correlations, the program no longer shows us the variance, because since the variance is in Fisher Z units, it would be misleading to present it on a table that just shows the correlations. But what the program does do is that it takes the lower limit of the correlations in Fisher Z units, converts it back to an actual correlation, which gives us 0.28, and it takes the upper limit for the Fisher Z units, converts it back to a correlation, which gives us 0.66. So that is the function of the Fisher Z transformation. As I said, it's just meant for behind the scenes. If you're not interested in pursuing that, you certainly don't need to. You can stick with the simple correlations, which is really all that you need. Let me show you a couple of other things that we can do over here. Each line over here obviously represents the effect size and confidence interval for a single study. And down here what we have is the effect size and confidence interval for the summary effect. We can click this tab which says one study removed, and now what we have on each line is no longer the effect size for that line. Rather, it is the summary effect based on all studies except for the current line. So for example over here, this effect size and confidence interval is the summary effect for a meta-analysis that uses all studies beginning with Newman and through Finch, but excluding Fanda. And this is the effect size and confidence interval for a meta-analysis that uses all studies except for Newman. And if you look at them, you can see that with all 6 studies in the analysis, we get an overall effect size of about 0.49. And that stays pretty much the same if we remove this one, or this one, or this one, or this one. But if we were going to remove this study, then the effect size would shift quite a bit to the right. If we were going to remove this one, it would shift quite a bit to the left. And so this allows us to identify studies that had a disproportionate impact on the overall analysis. And to see what that looks like, let's take a look at the study over here, Granger. And what we're saying is that if we did an analysis on the other five studies, and left out Granger, rather than getting a correlation of 0.49, we would get one of 0.56. We can actually do that. I'm going to come back here, click on Basic Stats. I'm going to click over here, select by study name. I'm going to deselect Granger, click OK, and the correlation that we see now goes to 0.56, the same number that we saw a minute ago. And I'm going to put that study back in, and it should be clear why that's happening. It's simply because Granger was the study which is way out to the left, so it stands to reason that when you remove that study, the overall effect is going to shift to the right. One other thing that we can do is we can click on this column called Cumulative Analysis, and what's going to happen now is the analysis that we're seeing over here is an analysis based on the first study, same as it was before. The analysis we're seeing over here is an analysis based on the first two studies. This is a meta-analysis based on the first three studies, 4, 5, and so on. And so, of course, the one over here based on all 6 studies is going to be identical to the one that we see over here. Why would you want to do something like this? Well, in this case, it doesn't make any sense. Where it does make sense is if the studies are sorted chronologically, and I'll be showing you in a later lesson how you can do that. Then basically what you're saying is, as of, for the sake of argument, 1990, when the first study was done, this was the cumulative evidence that we had. And you can see how the evidence shifted over time. In 1992, it looked like this, in 93, and 94, and so on. So you get a sense of how the information or the conclusion that we would have reached had we done a meta-analysis at some point in the past, how the picture, how the landscape shifted. That's true if you sort the studies chronologically. You might also sort them by something else. For example, you might sort them by study size, so that you have the very large studies at the top and the smaller studies keep at the bottom. There is evidence that in certain kinds of studies, the smaller studies tend to give us a larger effect size than, the smaller studies tend to give a different effect size than the larger ones. And you might want to know if the effect size actually shifts as we move from the larger studies to the smaller ones, and if so, how much it shifts. If you sort the studies by study size, going from large to small, and you can see how the point estimate shifts as more and more studies are added, you can see whether it is true or not that the effect size actually appears to be shifting, and if it is shifting, how much it's shifting, whether that shift is trivial or whether it actually can have an impact on the conclusion that we're likely to reach. So that's something else that you can do that is sometimes helpful. Let me point out one or two other things that I don't think I covered yet. One of them is that when you're looking at correlations, these confidence intervals around the point estimate are not exactly symmetric. So for example, over here we have a correlation of 0.5. The lower limit is 0.22, which is about 27 points below this, whereas the upper limit is 0.702, which is about 20 points above this. So we have more of a span on the lower end than we do on the upper end. I wonder if you can see that a little better if I shift this over. This line is longer than this line. It would be another way of putting that. And the reason for that is that when we're dealing with correlations, the confidence interval actually is not symmetric about the mean. What we do is we convert this to a Fisher z-score, we compute the confidence interval that way, and then reflect it back on the correlation. So that is not a mistake. That's actually the way things are supposed to be working. Something else that sometimes causes confusion is if we come over here to the next table, these statistics over here, the heterogeneity statistics and both the Q value, P value, I square, tau square, are shown on the top line. And one of the questions that I get fairly frequently is, these apply to the fixed effect model, what about the random effects model? The answer is that all of these heterogeneity statistics actually apply both to the fixed effect model and to the random effects model. They apply to the fixed effect model in the sense that all of these numbers are computed using the fixed effect weights. And they apply to the random effects model in the sense that once these numbers are computed, the Tor square, for example, is then used to assign weights so that we can compute the random effects model. Tor, which reflects the dispersion of the true effects, only applies to the random effects model because under the fixed effect model, we are asserting that there is no dispersion in the true effects. I squared, which tells us what proportion of the observed variance reflects real differences in the studies. Again, while it's computed using fixed effect numbers, fixed effect weights, only applies to the random effects model because under the fixed effect model we're saying that none of the observed variance is real, 100% of it is error, so this number only makes sense in the context of a random effects model. The Q statistic, I guess you can say, applies to both models because Q is the basis of computing I squared and Tor squared, and therefore it affects the random effects model. But the Q statistic, along with its degrees of freedom and p-value, really test the hypothesis of homogeneity, which is the hypothesis on which the fixed effect model is based. So in this case, for example, we're saying that the fixed effect model is not viable because if the fixed effect model was true, we'd only see this amount of dispersion less than one time in 1,000 analyses. I do want to iterate a point that we make in the book, which is that it is not the decision to use the fixed effect of the random effects model should not depend on whether or not this value over here is statistically significant. It should depend on the sampling method that was used to find the studies. So, for example, if you went to the literature and collected 6 studies addressing a particular question, conceptually or logically it makes sense that those studies are not really identical, and the effect size really does vary. The true effect size really does vary from one study to the next, and therefore the random effects model is a more plausible fit for the sampling, for the way the studies were sampled, than is the fixed effect model. So even if the p-value here was nowhere near significant, in the example that I gave, the random effects model would make more sense. Coming back over here, I think I've covered the key issues that I wanted to cover. Let me point out that there are many additional videos, and one of them I go into more complex analyses, including, for example, comparing subgroups. Let's say that you have a group of studies that gave you the correlation between 2 variables for males and a second group that gave you the correlation for females, and you want to see if the correlation is greater for males than it is for females. I'll explain how to work with multiple outcomes. So, for example, if each study gives you the correlation between self-esteem and math, and it also gives you the correlation between self-esteem and reading, how you can deal with the multiple outcomes. What if you have data for multiple time points or things of that sort? I'll show you how to do that. I'll show you how to work with meta-regression, how to assess the possibility of publication bias, and a number of other things. So I hope that you will join me for these other lectures as well. Our website is www.metaanalysis.com, and thanks for joining me.